Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronics Engineering. So in today's class, we are going to discuss about the network topology. We can also call as a graph theory in the electrical circuit. So here the graph theory in the computer science and here the graph theory in electrical circuit, both are different. So before going to discuss about the actual concepts in the network topology or the graph theory, so we should know the terminologies which we are going to use in this graph theory. So which means why this is called as a graph theory or network topology. Okay, so here we are representing the electrical circuit in terms of a graph. Okay, we are representing the electrical circuits in terms of a graph. Then how we can convert the electrical circuit into the graph, that here we will know. So first we should know what is mean by the graph, right? So here I have mentioned a definition. Let me read the definition of the graph. Here the graph consists of a set of nodes connected by branches. In graph, a node is common point of two or more branches. Okay, sometimes it may be only the single branch may connected to a node. A branch is a line segment that connected two nodes. So which means here, let us take the circuit. In this circuit, first let us identify how many nodes are there. So here, as you can see, the nodes are indicated with the green dots. So this is node 1 and node 2, node 3 and node 4. So in the graph also, just place the nodes, okay, as it is in a plain sheet. So let us indicate the graph 1, the same nodes 1, 2, 3 and 4. Right? Then the network can be converted into equivalent graph by replacing the passive elements and the voltage source with short circuit. The passive elements means the resistors, inductors or the capacitors. But anyway, in the given circuit, only the passive elements are the resistors and the voltage source. Right? So here, let us see in between 1 and 2 nodes, there is a branch which is having the passive element which is the resistor. So here, according to the rule, how we can convert the network into the graph? Okay, we should replace all the passive elements and as well as the voltage sources by the short circuit and the current source is replaced with the open circuit. So which means here, in between node 1 and 2, there is a passive element which is the resistor R1. Just replace this R1 with the short circuit. So here, let us draw like this. Next, in between node 2 and 3, okay, again there is a passive element which is the resistor R2. So again replace this with short circuit. Again 2 and 3 short circuit. Then in between 1 and 3, again there is an passive element which is resistor R4. Again replace this R4 with short circuit here like this. So in the graph there is no rule like we should draw a straight line. Okay, because this is a graph. Okay, we can just draw with our free hand. Even we no need to use the scale to get a straight line. Okay, so we can draw with the free hand. So next, in between 2 and 4 again. In between 2 and 4 there is an R3. So just join 2 and 4. And again in between 1 and 4 there is a voltage source. So according to this condition, the voltage source also should be replaced with the short circuit. This one. Then here, in between 3 and 4, there is a current source, but according to this rule, the current source with open circuit. So that's why here just we are not connecting this 4 and 3. So which means this is an open circuit. So this is how we can convert the network into the graph. Okay. So first we should indicate, we should just identify how many nodes are present in that particular graph, in that particular given network. Okay, then the same nodes we should just represent in a plain sheet. Then after that, you just replace the passive elements and as well as the voltage source with the short circuit and the current source with the open circuit, right? So here, of course, in the same network, okay, we usually, identify how many number of nodes and how many number of branches. Okay, so here the nodes are anyway 4. Okay, but when coming to the branches here, as you can see, of course, the 4 resistors are connected to the 4 branches, and another branch is with the voltage source, and another branch is with the current source. So total 6 branches are there. But when coming to the equivalent graph of the given network, okay, but it consisting of course the number of nodes are same as with the given network, but when coming to the branches are 5. So which means here the graph always contains, okay, the nodes are always same as that contains of the electrical circuit, but when coming to the branches, okay, so sometimes it may be equal or less than or equal to the number of branches present in the given electrical circuit, right? So this is the way to convert the graph, the network into the graph. Okay, now of course just now we have seen what is mean by the graph. Okay, so here the number of nodes present in the graph will be equal to the number of principal nodes present in the electrical circuit. Okay, here we should remember the point here. We should not just consider a node. Okay, we should consider a principal node. Okay, we know already what is the difference between the node and principal node. So node means only the point of intersection of two branches. Okay, but principal node means more than two. Of course, sometimes if that a particular branch, there are no more than two, then we can consider the normal node also. And the number of branches present in the graph will be less than or equal to the number of branches present in an electrical circuit. That's what just now we discussed, right? Then there are various types of graphs are there. Okay, so one is the connected graph and unconnected graph. Okay, and direct graph, undirected graph, right? And there is a planar and non-planar graph is also there that we will discuss later, right? So, and let us discuss one by one what is mean by the connected graph and what is mean by unconnected graph, and similarly what is direct and what is undirected graph, right? So first here you can see I have represented the various what is the graphs. Okay, in the first case this is called the connected graphs, and this is unconnected graph, and this is direct graph, and this is undirected graph, right? So why this graph is called as a connected graph? So here connected graph is nothing but if there exists at least, okay, one path from each node to every other node in the graph, then that particular what is the graph is said to be a connected graph. Which means here how many nodes are there? 4 nodes are there, right? So first let us start with node 1. So just to check whether there is a at least one path, okay, from this particular node to all other nodes. What are the other nodes? Node 2 and node 3 and node 4. So let me check from the node 1. Okay, so is there any path to the node 2? Yes, of course, this is the path to the node 2. And then node 3, of course, this is the path to the node 3. And for the node 4, this is the path to the node 4. And similarly, from node 2, okay, what are the other nodes? 1, 3 and 4. So is there any path from node 2 to 1? Yes, this is the path. And 2 to 3, this is the path. And 2 to 4, this is the path. Then similarly from 3 to all other nodes, okay, at least one path. Of course, if there more than one path is also no problem, but at least one path should be should contain. Then from 3 to 1, this is the path, and 3 to 2, this is the path, and 3 to 4, this is the path. So which means at least one path from each node to every other node. Okay, so each node from 1 to the remaining other nodes, and from 2 to the remaining other nodes, okay, and from 3 to the remaining other nodes. Then we can call it as the connected graph. This is called as a connected graph, right? Then coming to the what is mean by the unconnected graph, right? So unconnected graph means if there exists no path from each node to every other node, then that is an unconnected graph. So which means the graph either be connected or unconnected. If there is a path from each node to all other nodes, then that is a connected path. Okay. So if there is no path from each node to every other node, because as you can see, the same graph, okay, if suppose if it is like that, because here node 1 is there, from node 1 there is no path to node 2 and there is no path to node 4. So which means this is not a connected graph. Then what is it? Unconnected graph. But of course from node 2 to, again, there is no path for node 1, and from node 3 there is no path for node 2. I mean, from node 3 there is no path for node 1. So that's why this is a unconnected graph. Okay, then coming to the directed graph. Coming to the directed graph. Okay, so directed graph is nothing but, if in the given graph, okay, if they indicate the direction for every branch, then that is called as a directed graph. Which means, suppose here let us consider this particular graph. We don't know whether this path is from 1 to 3 or 3 to 1, because there is no direction indicated for this particular path. Okay, here path is nothing but the branch. Okay, so but here in the figure, let us consider this is figure 1. Let us consider this is figure 1. Okay, and in and this is figure 2 and 3 and 4. So in figure 3, of course, here clearly indicated the path for this particular branch is from 1 to 3. And here for the branch A is 1 to 2. And here for the what is that, branch C is 1 to 4. So like that, the direction for every branch is indicated. Then that is called as a directed graph. Then undirected graph is nothing but, if there is no direction indicated for all the branches, then that is called as a undirected branch, because here we don't know whether the current is flowing from point 1 to point 3, which means node 1 to node 3 or node 3 to node 1. So that's why this is undirected graph, right? So connected graph and unconnected graph, and directed graph and undirected graph, which means, suppose if it is not connected graph, then it should be unconnected. Okay, if it is not directed, then it is undirected, right? The opposite way. Now let us see subgraph. What is mean by the subgraph? The subgraph, the name itself, it giving the definition. Okay, so some part of the graph is called as a subgraph. Okay, or a part of the graph is called as a subgraph, right? So then how to get the subgraph? Of course, usually by removing the branch. Okay, one or more than one branch or a node, or sometimes even the combination, the branch and as well as the node, so that we can form a subgraph. So as we know, of course, because we are removing, how we are making the subgraph? By removing either the branch or the node, or some cases the both branch and node. Okay, so which means the subgraph will always contain the number of nodes and branches less than the main graph. Fine. Then when coming to the, what are the various types of subgraphs here? And the types of subgraphs are tree and co-tree. So which means, when a subgraph is called as a tree, and when a subgraph is called as a co-tree, because for a particular graph, okay, we can get some n number of subgraphs. Okay, but in those n number of subgraphs, okay, what kind of subgraphs are called as a trees, and what kind of subgraphs are called as a co-trees, that we will see here. Then first, when coming to the tree, here tree is a connected subgraph of a given graph which contains all the nodes of the graph, but there should not be any loop in the graph or any loop in the subgraph. Okay, so here how we can form the subgraph? Here the subgraph should contain all the nodes, that is the condition. Okay, when the subgraph is called as a tree, okay, so that subgraph should contain all the nodes, but it should not be any closed loop containing in that subgraph, then we can call it as a tree. And the branches of that particular tree are called twigs. Okay, so this is a graph, and let us draw a subgraph. Okay, so just by removing one or two branches, because according to the tree, the subgraph must contain all the nodes. So that's why here that we are not removing any nodes, just we are removing the branches, okay, to form a subgraph, and we will check whether the subgraph is either tree or a, what is that, tree or a co-tree, right? So here in the subgraph we are just removing the branch A and as well as the branch C. So let us check the condition whether this subgraph contains all the nodes of the main graph or not. So how many nodes are there in the main graph? 1, 2, 3, 4 nodes are there. And in the subgraph is also 1, 2, 3, 4 nodes are there. So the first condition is satisfied. This, it contains all the nodes of the graph. Then it should not be any loop. Of course, here you can see there is no loop here. Suppose if we just if we are not removing this, let us consider here the D is there, then it should not be a, then it is not a tree, because here this is a closed path. Okay, so according to the definition, the tree, okay, or a subgraph that contains all the nodes and there should be no any loop, then we can call it as a tree. That subgraph is called it as a tree, right? Otherwise, suppose let us just indicate this one also. Okay, if you consider this branch A also, then again this is a loop. So which means this is not a tree. This is this is simply a subgraph. This is not a tree. Okay. Or otherwise, if you just draw this one, again this is loop. So that's why this is also not a tree, right? Then of course for a particular graph there is no condition like it should be having only 1, 2 or 3 trees. Okay, so let us see how many number of what is that trees that we can get for this particular graph. So this is another combination. So this is also a one subgraph and this is also the second subgraph. So this second subgraph is also, we can call it as a tree. And when coming to the third one, by removing A, B, C. And fourth one by removing A and B and also F. And then fifth one. Okay. So how many subgraphs are there? Or not subgraphs, how many trees are there for this particular graph? There are 5 possibilities. The 5 possible trees are there for this particular graph. Okay. If we get, we can draw some more, but it should satisfy these 2 conditions. One is it should contain all the nodes. Another one is it should not have any closed loop. Right. So this is about the definition of the tree and how to draw a tree for a particular given graph. Then coming to the subgraph. What is mean by subgraph is which is formed with the branches that are removed while forming a tree. So which means here, what are the branches that we are removed to form tree 1? These are the branches. Like let me draw with the dotted lines. Okay, so these A, C, D branches that we are removed to form a tree 1. So according to this definition here, co-tree is a subgraph which is formed with the branches that are moved while forming the tree. Okay, branches that are removed while forming the tree. So here in the first tree, what are the branches that we are removed to form a tree? A, C and D. So which means here this A, okay, and this C and this D. So here nodes 1, 2 and 4. So for the what is that subgraph? There is no condition such as it should contain all the nodes of the main, all the nodes of the graph, right? So here it may or may not contain all the nodes of the graph. So here this is one code tree, right? So here this is one code tree, because before in this case by removing A, C, D we form a tree. So which means here the removed branches, okay, are the code tree. And here it may or may not be a closed loop, okay, but many cases it is a closed loop. Then coming to the second combination, here what are the branches that we are removed? This one, B and again D, and again E. So this is one core tree. And here this one, 1, 2, and 3. This is one core tree. And here A, B, and F. This is one core tree. And this one A, E, and B. This is one core tree. The same core trees here they have represented. You can see this is first core tree, and this is the second core tree, and this is the third core tree. As you can see here, 1 and 2 are the closed loops, but 3 is not a closed loop. So there is no condition like, okay, so it should have a closed loop or it should not have any closed loop. Okay, either it may have or may not have the closed loop. And coming to the nodes also, it may or may not consider all the nodes, because as you can see in the first and second subtree, of course 1, 2, 4 nodes only considered, but in the third subtree 1, 2, 3, 4 all the nodes are considered. Okay, so that's why there is no condition such that it should contain all the nodes, or it should not, or it should be or it should not have any closed loop, or it should have any closed loop, right? Then this is a fourth one, and the last one is the fifth one. This is the core tree. And in this core tree, okay, the branches, which means how many branches are there in this first core tree? 3 branches. The branches names are called A, C, D. And these A, C, D are called as a links, or we can also call as a chords. Links are chords, right? When in the tree, the branches are called as a twigs, but in the core tree, the branches are called as a links or the chords, right? This is also important because in the further topics, we are going to use these terminology. So that's why these are very, very important. What is mean by link and what is mean by chord, or what is mean by twig. Fine. Then of course here the links is equal to, okay, here B minus N plus 1. Here B is number of branches and N is number of nodes. So that by using this equation, we can find how many links are there in a particular, what is that, core tree. Fine. Now, okay. Now let us take one example. This is a given network. This is the given network. So how this network can be converted into what is that graph, and for that particular graph, okay, how to identify the trees and core trees, right? Fine. So here let us identify how many principal nodes are there for this particular given circuit. Of course here they have already given, okay, so this is node 1, and this is node 2, and this is node 3, and this is node 4. So let us indicate the same, like here node 1 and node 2 and node 3 and node 4. So 1, 2, 3 and 4. Right. Now in between 1 and 2, how many branches are there? So whether the branch having the passive element or voltage source or the current source, right? So in between 1 and 2, how many branches are there? Only one branch is there, and that branch is having the passive element, which is resistor. So according to this graph theory, so all the passive elements are replaced with the short circuit. So then one short circuit. Then next, in between 1 and 3, okay. So in between 1 and 3, again only one resistor is there, that is passive element, which is 30 ohms. So we can replace in between 1 and 3 also one short circuit. So 1 and 3. Next, in between 1 and 4, okay. So in between 1 and 4, of course, there is a voltage source, and these voltage source can be replaced with short circuit, right? 1 and 4. Then of course from 1 we have finished. Then 2, from 2 to 1 already we have drawn, and 2 to 3, again there is one element which is passive element. So this is also we should replace with the short circuit. Then 2 to 4, 2 to 4 is also only one element, and that element is passive element, and again we should replace that element with short circuit, right? Then 3 and 4, okay. In between 3 and 4, of course, so in between 3 and 4, of course, there are two elements are there. One is the passive element which contains 20 ohms. Okay, and another one is the current source. But according to the according to the condition to convert the network into the graph, okay, so only the passive elements and the voltage sources should be replaced with the short circuit, and the current sources is replaced with the open circuit. Of course, let us replace this passive element of 20 ohms resistor with the short circuit in between 3 and 4. And here, okay, again there is a 4 amperes, right? So this we should replace with the open circuit. So that's why we are not giving any other branch. Suppose let us consider instead of this here, let me just see there is a current source, voltage source here again. Let us consider this is 4 volts. Then in between 3 and 4, one passive element of 20 ohms resistor is there, and one voltage source of 4 volts, 4 volts is there. Okay. So which means 3 to 4, how many short circuit we should draw? 1 and 2. So which means again 3 to 4, one more short circuit is there. Okay. But in the given circuit, this is current source. So that's why we didn't join the second part. Right. Then this is a graph. Whether it is a, what is that, directed graph or undirected graph? This is undirected graph because here the branch currents, okay, we are not indicating the path for the branches, right? Suppose then how to identify or how to draw the, a path for that particular branch, okay. So that is also based on the given circuit. If the given circuit, suppose let us consider in the given circuit, if they indicate the direction of the current flowing through here, okay. So let us consider here also in this way, okay. And here let us consider this way, and here let us consider, of course, fine, okay. So as you can see, in between 1 and 2, the direction is from 1 to 2, so that's why we should indicate like this. And between 1 and 3, the direction is this, like this, 1 to 3, okay. And here 2 to 3, like this, and 2 to 4 is like this, okay. And 1 to 2 is like this, let us consider. And then 3 to 4 is again like this, okay. Of course, anyway, in the given circuit, okay, there is no current source, so which means this is also not. So now this will become as a directed graph, okay. So this is how we can convert the electrical circuit into the graph, okay. Of course, this graph is same like in the previous case that we are considered. So that's why for this particular graph also you will get the same number of trees, which are the 5 trees, okay, and again the 5 co-trees that you will get, okay. And next, based on these basics, okay, so now we are going to write the incidence matrix, okay, and as well as the basic tie set matrix and the basic cut set matrix. Then how we can form the incidence matrix and basic tie set matrix and basic cut set matrix. So here the incidence matrix is represented with a letter of A, and the matrix A is having, okay, the n cross B matrix, which means here n is the number of rows and B is the number of columns, right? So here n is nothing but the number of nodes and B is nothing but the number of branches. So based on number of nodes and branches, we can form a matrix. Then what are the elements of the matrix here? Okay, so usually in all these cases, the elements of the matrix having only either 1 or 0. Okay, and again this 1 is having +1 or -1 or 0. So then when we can consider the element as a +1 and when we can consider as a element of -1, and what is the condition to consider the particular element as a 0. So that is based on here plus and minus is based on the direction of the current from that particular node, which means if the direction of the current is towards the node, then we should consider that element of that matrix is +1. And if the element or if the direction of the current is away from the node, then we will give the -1, okay, to the other node. And suppose if there is no connection or if there is no direction of the current from that particular node to another node, then that is a 0. Okay, so by this way we can form a incidence matrix. Okay, so this we will discuss in the next class. Okay, what is incidence matrix and what is tie-set matrix and what is basic cut-set matrix. Of course, here basic, I mean, of course, the incidence matrix and basic tie-set matrix and cut-set matrix, all these we can write from the, or we can form from the graph, from the given graph, which means first we should convert the given electrical circuit into the graph. Okay, and then after that we can write these incident matrix and as well as the basic tie-set matrix and the cut-set matrix. Of course, here the basic tie-set matrix having the order of L cross B. Okay, so here L means, and here B. B is of course the name branches and L is the links here again, right? And in the basic cut-set matrix, here T cross B. So here T is the number of trees and B is again the number of branches. So which means here you can see in all these three matrices, the number of columns is same. The columns always represents branches, but the rows are, okay, sometimes in the incident matrix, the rows represents the number of nodes, and in the basic tie-set matrix, the row nodes represents the number of links, and in the basic cut-set matrix, the rows represents the number of trees. Okay, so this is the way to form the incident matrix, basic tie-set matrix and cut-set matrix. That we will discuss in the next class. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.